Good evening to all of you. Well, it's probably not evening, but it's evening for me as I'm recording this video. Hope that you are having a good day. So I'm going to give you a moment to work through this warm-up. You will need a graphing calculator today, or the graphing calculator app, or Desmos, something that you can use to help out with today. But go ahead and pause the video, take a moment to try this particular problem, and then I will give you the answer and then work through the problem in case you didn't get the answer. So hopefully you've taken a moment to pause the video and work through this problem. Your answer should be 2x cubed plus 6x squared plus 4x plus 4 plus 12 divided by x minus 3. So if you didn't get that, we're going to go through how to do that. If you did, you could go ahead and fast forward. So one thing you want to recognize is that you do not have a constant term, so you have to make sure you're adding 0 there. You must make sure that you have all the terms here. Also, you don't have a 0x cubed. And that's really important if you decided to use synthetic. If you decided to use long division, that's not required of you, but it's definitely helpful. But synthetic would definitely be the easier way to do that because we're dividing by x minus 3. So if we set that equal to 0, our a value is 3. So I'm going to put 3 in the box as my 0. We're going to have a coefficient of 2. That's x to the 4th. 0 x to the 3rd, negative 14x squared, negative 8x, and then 0 for the constant. Remember, we bring down the first term and we multiply. We add and we multiply. Again, we add and we multiply. Add and multiply. The last term is our constant. It's our remainder, not our constant. So this 12 is our remainder. So the 12 goes over whatever we're dividing by. So 12 divided by x minus 3. This is showing that x minus 3 is not a factor. Then we have the constant term, then we have the x term, then we just keep stepping up. So then it would be x squared, and then it would be x cubed. It makes sense that if I'm dividing x to the 4th by an x, I would end up with an answer that has an x cubed in it. So if you tried long division, same sort of process, just make sure you're subtracting, so you're distributing that negative sign. I'm happy to work through that with you if you tried that and want me to do so. So just let me know and I will meet with you and work through. So this is our last section of the chapter. If you look ahead to what's going on next week, I know this is the last day for 2020 before a break. And so this assignment, I would spend a little time today working on in Pearson, but you're actually going to have a work day also on Monday as we return. So just might want to look at those weekly instructions because there are some things that you want to make sure you note in there. We will be testing next week is how it will work out. So notes for 2.5, zeros of polynomial functions. We are going to use the fundamental theorem of algebra to figure out how many zeros we have. We're going to find rational and complex zeros. So that's where those complex numbers, those I numbers came in. And we're going to use the linear factorization theorem to find polynomials with given zeros. So the first thing is the fundamental theorem of algebra. You can look in the textbook on page 332. But what it's saying is if f of x is a polynomial that has a degree of n, which is what we've been using, and is greater than 0, so we have multiple terms here, then the equation f of x has at least one, that's what you want to fill in, it has at least one complex root. And so what we know is that there's going to be n complex factors. So whatever the degree is, if the degree is 3, then there's going to be 3 factors. If the degree is 5, there's going to be 5 factors. So the idea of a complex root, remember complex is just real or imaginary. They don't have to be imaginary, but that's just the idea. It's saying that if you have a degree where n is greater than 0, so it's not constant, you're going to have these roots, these zeros. Remember, root is another name for 0. So the next thing we want to know is that if we have a polynomial of nth degree, then it has n complex zeros. That's just kind of another way of saying the fundamental theorem of algebra. So a polynomial of the 3rd degree has 3 complex zeros. Now, complex zeros always occur in complex conjugate pairs. So we want to write that down. They always occur in complex conjugate pairs. And we talked about complex conjugates back when we were dividing in section 2.1. So conjugate pairs, remember, are in the form a plus bi and a minus bi. So we could say something like 3 plus 2i and 3 minus 2i. Those are complex conjugate pairs. We can say 8i and negative 8i. Those are complex conjugate pairs. The idea is when you multiply them, you get a real number. You do not have any imaginaries left because they're in the form of kind of a difference of squares. So when you multiply them, you end up getting a squared plus b squared. So we're going to use that. So page 336, this is a problem from your textbook number 25. It's just going to ask you to find a polynomial function given this information. So I'll give you, as we look at this, we have n is 3. So we want to recognize that n is 3. So that means my degree is 3. I have 1 and 5i as zeros, but again, if I have a degree of 3, remember if it's a third degree, it's got to have 3 complex zeros if I include the multiplicities. So right now I only have 2, so there should be another 0 that I can find. And then also that f of negative 1 is negative 104. So we're given 3 different things here that are going to help us as we write this polynomial function, okay? So I'm going to rewrite the fact that n means degree. So we have a degree of 3. So again, I'm just going to write these 3 blanks. So if we have a degree of 3, we have 3 zeros here. So again, I know that one of them is x equals 1. I know that another one is x equals 5i. So based upon what we just wrote down back here, we know that if it has an imaginary number, it's got to come in a conjugate pair. So if it's got an I with it, it's got to have a pair. So if we know that x equals 5i is a 0, we also know that x equals negative 5i is also a 0. So that's something that we want to recognize. So what we're going to do from there is we're going to start writing our function, and we're going to have to come back to this last statement. We don't have enough information for that. So we're going to say f of x equals a. In this case, we don't know what a is. That's our leading coefficient. But we're going to start writing these zeros as factors. So if x equals 1 is a 0, remember x minus 1 is a factor. If x equals 5i is a 0, then x minus 5i is a factor. And if negative 5i is a 0, then x minus negative 5i would be a factor. And remember that x minus a negative would become x plus 5i. Remember, if you set those equal to 0, we should get those zeros that you have. So what we need to do is we need to do some simplifying because we can't have imaginary numbers in our polynomial. They're not part of a polynomial. So I'm going to start by multiplying those, and I'm going to keep them in parentheses because then I'm going to have to take the result times x minus 1, and then I still have that times a. So if we start distributing, x times x would be x squared. X times 5i would be 5ix. Negative 5i times x would be negative 5ix. Negative 5i and 5i would be negative 25i squared. So we want to notice that the 2 middle terms will cancel. And negative 25i squared, remember I squared is negative 1. So if I multiply it by negative 25, I get plus 25. So x squared plus 25. It's still multiplied times x minus 1. It's still multiplied by the leading coefficient of a. So then from here, what we can do is we can go ahead and multiply these two, because again, we're just trying to simplify what we have. So everything else is going to stay the same, but I'm still multiplying the result by a, so I still need parentheses here. So we're going to distribute x times x squared is x cubed. X times 25 is 25x. Negative 1 times x squared is negative x squared, and negative 1 times 25 is negative 25. So now we're at a good place. Okay, I've got it all multiplied out, but what I still need is I still need to know what a is. So that's what I have to find. So that's where this last point, this last information comes in. Remember that negative 1 is my x value, and then negative 104 would then be my y value, input, output. So this is the point on the graph, -1, -104. So remember again, it's x and then y. So we're going to sub that into our function, and that's going to help us find a. So the y value would be -104. Remember, y and f of x are the same thing. We don't know a, that's what we're solving for, but we're going to sub in a -1. So when I do that, I'm going to put it in parentheses. So -1 cubed plus 25 times -1 minus -1 that's being squared, and then minus 25. So I want to make sure that we're doing order of operations correctly. So -1 cubed would be -1. 25 times -1 is -25. -1 squared is 1, so it'd be -1. And then minus 25. That's going to equal -104. So order of operations would say to do our parentheses first. So -1 minus 25 minus 1 minus 25. You could use a calculator, but -25 and -25 is -50. And then I would have the two -1. So I get -52, but it's being multiplied by a. So this is the same as -52a. Don't think that it's a minus 52. That's why your parentheses are important. Okay, it's a times -52. So if I solve for a, I get that a is a +2. So I'm going to take that answer of +2, and I'm going to take it back up here, and I'm going to sub it in for a here. And then I'm going to use that to solve for my function. So I have f of x equals 2. I have to move this over so I have room here. Okay, so f of x equals 2 times x cubed plus 25x minus x squared. I'm going to have to go to the next line, minus 25. And you can put that in order now, or you can put it in order later. So we would get 2x cubed plus 50x minus 2x squared minus 50. So it just needs to be in order from highest exponent to lowest exponent. So 2x cubed minus 2x squared plus 50x minus 50. So that is our function. So in this case, we do have a degree of 3 if we highlight what we know. If we were to graph this, it would have an x-intercept of 1. You would not see the 5i and -5i because they're imaginary x-intercepts, so you're not going to see those. And then if you subbed in a -1 to this function, you would get out a -104. So that's what's going on there. Okay, so you're definitely going to see those. You're going to have some of those practice problems on that worksheet. Okay, so that's really the first objective here, is to determine the number of zeros and then be able to write a function with that. So now we're going to talk about how to, well, actually the first and the third, use the factorization theorem to find polynomials. So now we're going to focus on that second one, which is finding rational and complex zeros. So we're going to go back to the rational zeros test. So we're going to use, we're going to talk about this rational zeros test that you would have looked at last year, I believe. If not, I'm going to go over it for you. But basically, if you have a polynomial, so in this case, I have f of x, all this goodness, okay? So basically what this is saying is if you have a polynomial, then you can look at the factors of p, which are the factors of your constant term at the end, and divide it by factors of q, which is the ace of n term, which is the leading coefficient. And if you divide those, then you can find all the possible rational zeros of a function. So for this last one, if we would have done that, factors of 50 over factors of 2, and you would have found that 1 would have been in the list. 1 is always in the list, but you would have found that, okay? So this year, you're either going to be given one or more of the zeros and asked to find the remaining ones. We did some of that back in section 2.4. Or you're going to have a graphing calculator that you can find these rational zeros. Remember, rational zeros mean that they're either going to terminate or they're going to end. Okay, so you're going to want to fill those in. So you're going to be given one or more of the zeros and asked to find the remaining zeros. Or you're going to use a graphing calculator to find the rational zeros. Again, rational zeros cannot have repeating decimals. Okay, so when we talk about rational zeros, they're going to terminate or I should say they don't have repeating. They are non-repeating. So they're either going to, rational zeros will either terminate or they will end. Okay, they can be written as a fraction of integers. That's what a rational number is. So we're going to look at a couple of these. This is where your calculator comes into play. Or Desmos again. So I will show you that on my on my screen here, but it would be important for you to actually practice them as well. So if you're not given the zeros, this is help. I will also show you this rational zeros theorem in case you don't like using the calculator. Then I will show you how you can use that. So we are going to solve this polynomial equation. So back to what we talked about earlier, it has a degree of 4. So if it has a degree of 4, that means that we have 4 zeros. So we need to find all 4 of them. That's how we know that we're going to be done, is once we find all 4, then we can do this. So just to go back to this part here. Okay, again, remember it's factors of the constant over factors of the leading coefficient. I'm going to go ahead and write that down. And that's going to help us find possible rational zeros. So just to try that again, so we would take factors of 24. So if we're doing P over Q, we would do factors of 24. So we're going to do plus or minus because it can be positive 1 and positive 24 or negative 1 and negative 24. Okay, so we're going to say plus or minus 1 because it works, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 24. So 1 and 24, 2 and 12. I forgot 8, so we can also do 8. So 3, I was trying to write them in order. So 3 and 8, 4 and 6. So those are all the possible factors of 24. That's a pretty big number. That's where the calculator can definitely come in handy. Divided by factors of the leading coefficient. The leading coefficient is 1. So when I divide it by 1, it's not going to change any of these. So you can, if you want, go through all these. You could try 1 and negative 1. You could try 2 and negative 2, 3 and negative 3. You could keep going through all of these. You actually have, what, 1, 2, 3, 4, 5, 6, 7, 8. You actually have 16 to try because you have a positive and a negative. So you can keep trying those. And what I mean by trying them is you would have to divide using long or synthetic until you get a remainder of 0. That's when you know you have a factor. So if 1 is a 0, x minus 1 would be a factor. Or you can take the calculator out, again, graphing or scientific, and you can just graph and see if you can find the rational 0. Okay, well, my calculator doesn't want to work, so we're going to go to Desmos because that's not working. Okay, so we're going to type in, we just type in y equals. So we see that it's obviously touching the graph, touching the x-axis. That's what we want. You can't really see the rest of the graph, so you can go up here to the wrench, and I could change my y-axis. I'm going to make my y-max just be higher, so I'm going to make it go to maybe 30 so that I can try to see what's going on with the graph, because I want to see that it is kind of moving a little bit. And you can, the nice thing about your Chromebooks is you can zoom in and out, but that's how you can actually change it. So you can see this is what the shape of the graph looks like. But what we're interested in is we're interested in where it's touching or crossing the x-axis. Now, we said there's 4 zeros, but notice it's only touching the x-axis in one place. That means we either have multiplicities here, which we should recognize we do have a multiplicity here since it's touching, and that we also have imaginary zeros, complex zeros that are imaginary. Okay, so we're going to have to deal with those. So I'm going to draw just a quick sketch of this to remind me later of what's going on if I was going to look back at my notes. So my graph is looking something like this. So I want to recognize that because it is touching here at 2, my multiplicity is even. So I know that I have to have 4 zeros. So I know that I have to have x equals 2 at least 2 times. Maybe all 4 times, but definitely 2 times. Probably not all 4 since there's another turn in the graph, just FYI. So what we're going to do is we're going to use long division or synthetic division. If x equals 2 is a 0, then x minus 2 is a factor, and it would occur twice. So I'm going to use synthetic. You can use long if you want. We're going to get more into long in the next chapter. So I'm going to use my coefficients. And remember that if I skip a degree, like I skipped an x cubed, I'm going to put a 0 in its place for the coefficient. So x to the 4th, x cubed, x squared, the x, and the constant. You might just think about those as you're writing them down. Going to bring the first one down and multiply. Remember, then we add. And think about this. If we know that 2 is a 0 on the graph, it should give us a remainder of 0. So if you're not getting that, that's telling you that you have some error somewhere in your problem. So again, you see that I have a remainder of 0. So what I'm going to do is I just divided by x minus 2. So I took this original polynomial and divided it by x minus 2. So it's giving me an x cubed graph, x cubed plus 2x squared minus 2x minus 12. So I'm going to ignore my remainder, and I'm going to divide by the next x minus 2. So I'm going to use these values again, and I'm going to do it with 2 again, because I'm dividing by the second 0 of 2. So again, since we know it was even because it touched over here, we know this should also give me a remainder of 0, which it does. And so what I have remaining is, remember, 6 is the constant, 4 would be the x, and the 1 would be the x squared. So this is what I have left when I divide it. Now remember, I divided by an x minus 2 and another x minus 2. So this is what I have when I take this x to the 4th graph and I'm factoring it. This is what I would get. Again, it doesn't matter the order that you put them in, but that's what you're getting. So this x minus 2 is giving me a 0 of 2. This x minus 2 is giving me a 0 of 2. So I have 2 occurring twice, has a multiplicity of 2. But what I have to find is I have to find the other 2. So I can try to factor or use the quadratic formula on this quadratic. And if you try to factor it, it's not going to factor. So we're going to have to use the quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we have 16, and then it's 1 negative there, so it's going to be 16 minus 24 all over 2. Go out to the side here, so we get negative 4 plus or minus the square root of negative 8. 16 minus 24 is negative 8. So then I'm going to simplify the square root of negative 8, so I can take out a negative because it's negative under the radical. So a negative 4 times a positive 2. So I'm going to get negative 4 plus or minus 2i, because the square root of negative 4 is 2i, square roots of 2, all over 2. And then we have to divide those. So again, you can choose how you do it. You could take out a GCF. So you could take a 2 out of each of these, so you can divide by the 2 at the bottom. So you'd have negative 2 plus or minus I square roots of 2. All divided by 2, and the 2's canceled. Or you can divide each of these by 2. So your other option is to take -4 divided by 2 plus or minus 2i squareds of 2 divided by 2. So those 2's would cancel, and -4 divided by 2 would give you -2. So it's really up to you on how you want to do it. So you would get -2 plus or minus I squareds of 2. So that gives you your answers. So you have to have 4 of them. So we want to make sure that we have 4. So we're going to list them out. We have x equals 2. It has a multiplicity of 2. So there's 2 of them. Then you have x equals -2 plus I squareds of 2. There's another one. And then you have -2 minus I squareds of 2. Remember, it's -2 plus or minus. So you can write it together, and Pearson will allow that as well, but you can also write it separately and recognize that you have 2 of them because of the plus or minus. So those would be your other 2 zeros. I didn't write them up here, but those would be the other 2 zeros that would fill in all 4. And that's why you don't see it crossing the x-axis or touching it, because they're imaginary. So you're not going to see them in that case. Okay, we're going to try one more like that. So we're going to solve this polynomial equation. Again, since we're not given any of the zeros, we are going to use our calculator to help us. Again, you could do factors of p over factors of q. So if I'm just going to show you this if you don't want to use the calculator. So factors of p would be plus and minus 1, plus and minus 6, plus or minus 2, plus or minus 3. That's all you would have there. And then q would be plus or minus 1 and 4, and then 2 and 2. So what you have to recognize here is that you would have 1 divided by 1, which is 1, but then you have 1 divided by 2, so you can get 1/2. You have 1 divided by 4, which is 1/4. Then you have 2 divided by 1, which is 2. 2 divided by 2 is 1. 2 divided by 4 is 1/2, so you have some repetition there. Then you have 3 divided by 1, so that's 3. 3 divided by 2 would be 3/2. Hopefully you get the idea. So these would be all your possibles. Now remember, back here, our possibles were divided by 1. So it was just all those in the list. And notice that 2 was the 0 we used because that's where it was touching, and that was a rational one. The other ones would not be rational, they're complex. So as we use our calculator, we should be seeing 1 or more of these. Remember, we have a degree of 4 again, so we need 4 total zeros. So I'm just going to list them out so we recognize that. And what we want to get from our graph is we want to get 2 of them. Just like back here when we were able to get the multiplicity of 2, that represented 2 zeros. And whenever we have 2 zeros, we're able to get our final answer down to a quadratic. That's our goal. So we need to find 2 of them from the graph. So again, we're going to go back to either our graphing calculator or Desmos. Okay, we're going to type this in. So 4x to the 4th minus x to the 3rd plus 5x squared minus 2x minus 6. Again, you may have to change the window a little bit. Okay, so you can either zoom in and out, or you can just go up here and change it. So maybe I want to go by ones here. Maybe I want to go from -10 to +10 on the y's. Maybe I want to go from -10 to +10 on the x's. Okay, whatever you need. Obviously, I don't need that many x's, so again, you can zoom. But what we're looking for is we're looking for where they're crossing or touching the x-axis. And this does look like a parabola. If you zoom out, it does just kind of look parabolic here. It's not, but that's what it looks like. So we see that it's crossing at 1. So that's going to be an odd multiplicity. So it's either going to occur 1 time or 3 times. If it was going to occur 3 times, guys, it wouldn't look like it's just crossing through. It would kind of jog a little bit. And I also see this one over here, which is -0.75. So as a fraction, that's -3/4. So there's the 2 that I need. They don't touch, so I need 2 separate ones. So one of them is x equals 1. The other one is x equals -3/4. So it doesn't matter the order. But notice, here's where we would have had 1. And then if I would have kept going here, plus or minus 3/4 would have actually been the next one. Okay, 3/4. So -3/4 would have worked there. So now what we're going to do is we're going to use synthetic, and I'm going to start with my non-fraction. So I'm going to start with 1. I'm going to put my coefficients here. So a degree of 4, a degree of 3, a degree of 2, a degree of 1, and a degree of 0. So make sure you have all of those. Remember, since x equals 1 was the 0, we should be getting a remainder of 0. Can't say that enough times. And there we go. We get a remainder of 0. So we just divided by x minus 1. That's what we did. We divided this original polynomial by x minus 1. And we were able to get this remaining polynomial. 4x cubed plus 3x squared plus 8x plus 6. That's the idea of what's going on here. So now I'm going to take my remaining polynomial, these 4 terms, and I'm going to use it with negative 3/4. So I'm going to bring down the 4. I'm going to multiply negative 3/4 times 4. So that's like negative 3 times 4, which is negative 12. And then I'm going to divide it by 4. So I'm going to get negative 3. I'm going to add those and get 0. When I multiply, I get 0. That's easy. Add, I get 8. 8 times negative 3 is negative 24. Divided by 4 is negative 6. So again, I should get a remainder of 0. And you might be thinking, well, what's this factor? Well, this factor you could say is x plus 3/4, which we typically don't factor with fractions. That's the same as 4x plus 3 if you multiplied both things. So remember, you'd subtract 3 and divide by 4. So now, here's my remainder of what I have left. 4, 0, and 8. So 8 is the constant. There's no x term, so I have 4x squared plus 8. So that's what I have left to solve. Okay, so again, I have these factors. I had a factor of x minus 1. I had a factor of x plus 3/4, or 4x plus 3. And then I have this 4x squared plus 8. So I'm going to solve this. So 4x squared plus 8 is equal to 0. You can try to factor it. There's not going to be much that factors. You can use the quadratic formula. The b value is 0. Or since you don't have an x term, remember the x term was 0 here, you can solve by square roots, which we did back in the quadratic section. So I can subtract 8, can divide by 4. So x squared is negative 2, and I can take the square root. So I get plus or minus, don't forget plus or minus, the square root of negative 2. So I can take the square root of negative 1 out. The square root of negative 1 is I, and then I still have the square root of 2. So remember, that's 2 answers. That's why a quadratic here, when you have a degree of 2, should be giving you the 2 answers with the plus or minus when you put the square root in the problem. That's what's happening there. So our answers are x equals 1, x equals negative 3/4, x equals I square roots of 2, and x equals negative I square roots of 2. So there are our 4 answers, 2 of which are imaginary, which is why you did not see them show up on the graphing calculator, because they were imaginary. Okay, so those would be our other answers, I square roots of 2 and negative I square roots of 2. Those are our other zeros that we were looking for. So there's the 4 of them. So that's what's going on. So trying to recognize, again, that you can use your calculator to help you find some rational zeros. Again, zeros that terminate or repeat on the calculator there. Those are rational, and then from there using synthetic division, or if you want to, long division, so that you can find all zeros. So your homework here, you have 2.5, you have a worksheet that's going to have you find some polynomials and find some zeros here, just trying to see that you can do it from scratch. So there's only 2 problems. I took some off there, so you have a couple problems there. And then you have a short assignment as well in Pearson. So if I can be of any help, please let me know. Have a good day.